The next part of lecture 9.5 that we are going to take a look at is going to be how to collect gas over water. The reason why we are looking at this because in reality, most of the reaction that we are going to deal with is going to involve with aqueous solution. And when there is the formation of gas that we are going to collect is going to include the vapor of water as well that is going to contribute to the overall pressure of everything that is under that reaction. Okay, so you see example of this collecting gas over water before from the Alka-Seltzer lecture demo in chapter 9.2. Okay, so in this case, as you see, when sodium bicarbonate react with citric acid in the tablet of Alka-Seltzer, when it's dissolved in water, it's going to generate CO2 gas, right? And this gas right here is being collected within this balloon right here, right? So in this case, as the gas increase, right, you are going to see that the volume of the balloon will also expand as well. However, if I collect the gas using this method, it's going to be a little bit challenging to measure the volume of a balloon, right? So in this case, it's just not very convenient. In an actual lab, what you are going to do instead is you are going to use eudiometer to help you to measure the volume of gas that's collecting over water. Eudiometer is the tool that is used to measure the volume of gas. Okay, so it's going to look like a long, very long test tube. Okay, but this eudiometer will actually have marks on it. So these marks actually tell you about how many milliliter would that be. Okay, so pretty much if you see, let's say like if its mark is right here and it's say like 25, it's going to be the reading of the volume would be 25 milliliter. Okay, so that's what it means. Okay, so in this case, you are going to get to use the eudiometer in lab 4 when you are going to measure the value of the gas constant R. Okay, so what we learned in class, which is equal to 0.0821 atm times liter over mole times Kelvin. Okay, so in this case, you are going to measure that. Okay, so it might come out to be close or it might be deviated from the theoretical value. You need to also think about the source of error that would come with that as well, right? So you are going to see how to measure this in lab. Okay, so the idea of eudiometer is that you are going to fill water all the way, right? So fill up of this eudiometer with water. Okay, before the reaction start, the water will fill all the way to the brim. Okay, so what happened once, so this is where the reaction occurs. Okay, so once the reaction occurs, it's going to generate a certain type of gas, right? It depends on what reaction you are going to look at. So the gas that is being generated is going to be trapped within this eudiometer. Eventually, the gas will rise and it's going to displace the water inside the eudiometer, right? So it's going to push the water down. So therefore, at the end, you are going to be left with this volume of gas inside the eudiometer, and then you will be able to read the volume just on that mark of the eudiometer. Okay, so that's how we are going to measure the volume of the gas. Okay, so it's easier than using the balloon, or it's easier than using this flask right here. But what I would like to emphasize is that because the gas that is generated is going to be collected above water, and because water is going to evaporate eventually too. So therefore, in this case, the gas that is collected in here is not going to be just the gas that you are interested in anymore. It's also going to involve with the water pressure, the water vapor as well. Okay, because again, water evaporates. So therefore, in this case, within this empty space right here is going to contain the gas that you are collecting and also water vapor as well. Okay, so that means in this case, because we are looking at the mixture of gases, therefore in this case, the total pressure within this flask right here is going to come from the partial pressure of gas and also the partial pressure of water vapor as well. Okay, so similar to the previous section that we learned before. Okay. Now, let's take a look at partial pressure of water. Okay, so again, when I talk about partial pressure of water, this is going to imply that this is going to be in gas form. Okay, so it's after it's evaporate, right? So that means in this case, because evaporation of water depend on temperature, you are going to see that the pressure of water is going to depend on temperature as well. Okay, so in this case, if you're looking at a high temperature here, right? So you're going to see that at higher temperature, you will see that the rate of evaporation would be faster, right? So water would evaporate more at a higher temperature. So therefore, in this case, you are going to observe a higher partial pressure at a higher temperature for water. Okay, so this table right here is very useful because you can know exactly what should be the partial pressure of water at a specific temperature. So for example, if you are looking at 25 degrees Celsius or 77 degrees Fahrenheit, you will see that the partial pressure of water would come out to be 23.8 torr. Okay, so that means in this case, when you are going to the experiment, if you want to know what is partial pressure of water, all you need to do is you need to just look up you just need to measure the temperature, and then you use that temperature and look up from this table. Okay, you do not need to memorize this table. This table would be provided on the exam for you to use. Okay, so I'm going to get into the example and how to use this table. Now let's take a look at calculation example 1. Okay, so pretty much this reaction is going to be the reaction of the alkyl sulfur again that we see earlier. Okay, so it's the reaction between sodium bicarbonate and citric acid that is eventually generate carbon dioxide. Okay, so what we are going to focus our attention on is going to be CO2. Okay, so because it's a gas, okay, so we deal with gas right now. So the problem asking you to find out number of mole of gas, okay, so find out N. Okay, is giving you volume, is giving you temperature, okay, and also is giving you pressure as well. So can I just use this PV equal and RT, plug everything in and get N? Okay, so because I already have all of this, the answer is no. The reason for that is because we are collecting this problem over water. Okay, so the keyword, I want you to jot this down. The keyword is you are collecting carbon dioxide, okay, over water. Okay, and this is inside the balloon. So that means the keyword is you are collecting gas over water. So that means in this case, you are going to have to consider partial pressure of water as well, right? Because if you think about it, the balloon that is collecting above water, this is going to be water is evaporate, right? So you're going to end up with water pressure in there. You're also going to collect CO2 gas that is being formed as well. So that means in this case, this balloon right here contain both. So therefore, in this case, you will need to make sure that if you are going to plug it in PV equal in RT, this pressure right here have to be only the pressure of CO2. Okay, it cannot be the total pressure. So therefore, in this case, we know that we cannot use PV equal and RT yet. We need to first find out what is the pressure of just carbon dioxide first. Okay, so that means the pressure that is given to you here from the barometric reading is going to be total pressure. Okay, so this is the total pressure of both carbon dioxide gas and also for the vapor of water as well. Okay, so in this case, what we are going to use is going to be the P total, right, equal to partial pressure of everything. So in this case, since we have only 2 gas, so you can just ignore those. Okay, so it's going to be one is for water and the other one would be for CO2. Okay, so these two add up would equal to the total pressure. Okay, so that means in this case, what I'm going to do is I'm going to go ahead, look up the partial pressure of water, right? Because we are given temperature. And as I mentioned earlier, if we know temperature, we should be able to find out the partial pressure of water as well. So in this case, it's giving us 6 degrees Celsius. So therefore, in this case, the partial pressure of water would be 7 torr. Okay, so you need to take 7 torr into account. So what you're going to do next is that we are going to set up 1.007 atm equal to pressure of carbon dioxide plus pressure of water. So in this case, if you do this correctly, you can see, right? So this is torr, this is atm. So you can add them, subtract them. So you need to make sure they are in the same unit first. So convert that torr into atm. Okay, if you do this correctly, you are going to get 0.0092 atm. Subtract that from 1.007, so you're going to get 0.9978 atm as the partial pressure of CO2. Okay, once you get this pressure, then the next thing is going to be plug that in to find out the number of mole. Okay, so by using the pip nerd. Okay, so what I'm doing is I'm just rearrange equation so that way the n is going, or the number of mole would be just on by itself. Okay, so in this case, again, because we are looking at CO2, so therefore this is going to have to be off CO2. Okay, so pressure have to be off CO2. So therefore, in this case, what you are going to do is just plug those in, right? So pressure of CO2 that we calculate earlier, and then divide that by the constant R, and then the temperature in Kelvin. Okay, so don't forget to change this into Kelvin. Okay, and also because R is in liter, so you also need to change this in liter as well. Okay, so everything have to base off the unit of R. If you calculate this correctly, you are going to get the mole of carbon dioxide gas equal to 0.0111 mole. Okay, so that would be your final answer. The problem might not ask you in mole, it might ask you in grams. If the problem asks you in grams, then you just need to convert from mole to grams by using molar mass. Right, molar mass will allow you to convert to grams of CO2. Okay, so that's how you do it. Next, example 2, I would like you to do this on your own. Okay, so I would like you to think about what equation you should use. And if you need to use partial pressure of water, I would like you to go back to page 49, right, to look at the table of the partial pressure of water. So let's pause the video now and complete this and resume the video again when you finish. All right, let's check your work together. Okay, so in this case, we are going to make hydrogen gas. Okay, so H2. Okay, so that's hydrogen gas by reacting zinc with hydrochloric acid. Okay, so in this case, it's giving you the fact that this gas is going to be collected over water. Okay, so that's the key word. Okay, so we have over water, so therefore in this case, somehow we need to find out the partial pressure of water. Okay, and it's telling us that this reaction is going to collect and it's going to have the total volume of 154.4. Okay, so this is the volume, and it's giving us that the total pressure is equal to, so this is P total, 742 millimeter mercury, right? And then this is going to be temperature. So again, asking you to find out mass of hydrogen gas. So that means in this case, you are going to somehow find out mole of hydrogen gas, and then from mole you convert to grams, right? Because mass is in grams. Okay, so that's going to be our idea here. So that means what I am going to use is going to be these two equations, except we are going to use partial pressure of hydrogen gas plus water, okay, equal to the total pressure. Okay, so if I do that, so let's take a look at pressure of water first. So it's at 25 degrees Celsius. So partial pressure of water would be 23.8 torr. So remember, torr and millimeter mercury are the same, right? It's 1-to-1 ratio. So in this case, you are going to get 23.8 millimeter mercury as. So now let's set it up. Okay, so now let's set it up here. So we have P total that is going to equal to P of the water, right, plus pressure of hydrogen gas. Okay, so in this case, 742 millimeter mercury is going to equal to, let's go back again, 23.8. Okay, so we're gonna have 23.8 millimeter mercury for water, right, plus partial pressure of hydrogen gas. Okay, if you solve for this, you are going to get partial pressure of hydrogen gas equal to 718.2 millimeter mercury. Okay, now the next thing that we are going to take a look at is we are going to plug this into PV equal nRT. Okay, so PV equal nRT. Again, I would like to know the N, right? So I would like to know number of moles. So I'm going to move RT to the other side, so that way I can get just N. Okay, so N would equal to PV over RT. Okay, so remember the pressure need to be in ATM because the constant R is in ATM. So therefore, in this case, I would need to convert this millimeter mercury into ATM first. Okay, so 760 millimeter mercury is equal to 1 ATM. Okay, if you do this, you are going to get 0.945 ATM as the pressure. Okay, so then the next thing we are going to do is we are going to make sure that temperature is also in Kelvin as well. If you add these to 273, you are going to get 298 Kelvin. And then we also need to make sure as well that the volume is in liters. So if you convert this into liter, so you are going to have 154.4 milliliter, right? So we know that there are 1,000 milliliter in 1 liter. So therefore, in this case, you are going to get 0.1544 liter as the volume in liter. Okay. All right. So after you get everything in the proper unit, you just need to plug all those in. So 0.945 ATM multiplied by 0.1544 liter. Okay. Divide by the constant R, which is 0.0821 ATM times liter per mole per Kelvin by 298 Kelvin. Okay, so if you do this, then make sure that you cancel the unit as well. So the unit should cancel out, right? So ATM cancel out, liter cancel out, Kelvin cancel out. So you're gonna have per mole. So that's this mole gonna flip up. Okay, so you're gonna get final answer in mole. Okay, so if you do this calculation correctly, you should get the value of 0.005964. Okay, so I'm not gonna round yet. Okay, so this is going to be in mole. Remember, we don't want mole, we want mass, right? So in this case, the next step that you need to carry on is going to be convert from mole to grams. Okay, so you're going to convert this from mole to grams. Okay, so we know that every 1 grams of hydrogen gas, remember hydrogen gas is going to be in diatomic molecule, right? So in this case, it's going to be in diatomic molecule, which is H2. So therefore, in this case, what you are going to use is you are going to use molar mass of H2. Okay, so if you add those together, you should get 2.016 multiply. So if you multiply these two values together, you should get 0.0120 grams of hydrogen gas. Okay, so now let's check our significant figures. Okay, so our sig fig should come out to be 3 sig fig. Okay, so again, even this is 2, but then you do the addition, right? So addition go with the least number of decimal places, which is 0 in this case. So you should get 298 Kelvin as the answer for the Kelvin. So this is gonna be 3 sig fig, right? So 3 sig fig of these are 3 sig fig as well. So therefore your final answer should come out to be 3 sig fig. So this is going to be your correct final answer, 0.0120 grams of hydrogen gas. All right, let's take a look at the summary of what we learned in chapter 9.5. Okay, so pretty much these are the equations that we learned so far in chapter 9.5, right? So we're looking at the mixture of gases. We're looking at that every gas going to contribute into the total pressure. If you want to know what is the total pressure, you're just gonna add all those gases pressure together, right? What we call partial pressure. If you add all those together, you're gonna get total pressure. And you also learn about how to collect gas over water as well, which means you need to make sure that you also account for the partial pressure of water when you deal with collecting gas over water. Right. So, and if you're using PIP nerd, right? So this one, you need to make sure that these are going to belong to specific gas, right? Unless you are looking at the total pressure and total mole, then you can just add all of them together. Okay. And then we also looking at the mole fraction of gases as well. Okay. So that's just the summary of this lecture 9.5. Please start working on your homework 9.5 as soon as possible. Okay, so to just reinforce your understanding. If you don't understand anything at all, or if you have any question, please do not hesitate to reach out to me. Okay, so visit me during office hour.